Hello friends, you are welcome to our general physics class today. The topic we're looking at is simple AC circuit. Of course, from our previous class we've already introduced this topic and we considered a circuit that consists of resistor. We also considered a circuit that consists of inductor, a circuit that consists of capacitor, individually, after which we looked at a circuit that is an AC circuit that contains resistor and inductor in series, resistor and capacitor in series. We established the capacitive reactance, the inductive reactance, which are the quantity that opposes current in this AC circuit. So today we want to now consider a circuit that contains all three elements. Is that okay? Resistor, inductor, and what? Capacitor. Our aim shall be to determine the current in the circuit. There are the peak current, the mean square current, and of course the reactance, which is the opposition to the flow of current offered by these three elements that we have in this AC circuit. Is that okay? Now take a look at the diagram here on the board. There is an AC circuit containing resistor, inductor, and capacitor in series. Across each of these elements, we have their voltages. So you have V sub R, the voltage across the resistor, V sub L, the voltage across the inductor, and of course V sub C, the voltage across the capacitor. Now, by the time you apply a voltage across this circuit, the voltage given as V sub 0 sine 2 pi ft, where f there is the frequency, it's going to drive in an instantaneous current. That instantaneous current is given by I equal to I sub 0 sine 2 pi ft. Is that okay? Now this V sub 0 is our peak voltage, also known as the maximum voltage. And then coming to that of current as well to I sub 0 is known as the peak current, also known as the maximum current. So this is what we're going to do quickly to look at the formula for calculating the peak current, the formula for calculating the mean square current, the formula for calculating the impedance, because in this case the combined effect of the opposition to the flow of current in this circuit due to these three elements that are operating there. That opposition to the flow of current is known as impedance. Is that okay? So here on the board we've got these formulas here that are important for us to get used to. We should memorize them. Is that okay? First hand, in dealing with our current, you know that we quickly have to remember Ohm's law, alright, which relates current to voltage and that element that opposes current, alright, which in respect to Ohm's law is the resistance. But you know that in this case, it's not only the resistor that is opposing current anymore. We have inductor, we have capacitor there. So it means the quantity opposing current, considering Ohm's law, will no longer be R alone, okay? We're going to put these three elements together, which is the opposition to the flow of current offered by the resistor. That opposition is known as resistance. We use R for it. We're going to consider the opposition to the flow of current offered by this inductor. We use XL for it. In our previous class, we referred to that as inductive reactance. Then, of course, we're going to combine the opposition to the flow of current offered by the capacitor. And that opposition, we use X sub C for it, which is capacitive reactance. The formulas we've actually established them from our previous class. Alright, let's look at equation 1, 2, and 3 as we have on the board there. Equation 1 defines the peak, the maximum current, I sub 0, and we obtain it using the peak voltage, the maximum voltage, V sub 0, divided by the impedance, Z. Is that okay? Now, Z, which is the impedance, considering these three elements here, has the formula given by equation 2. Z is equal to square root R squared plus open bracket XL minus XC, close your bracket, and then raise it to power 2. Please, dear friends, I want to emphasize in this, do not confuse this expression here, XL minus XC in bracket raised to the power 2. Don't confuse it with this. They are not the same thing, please. They are not the same thing. So I am going to mark this wrong. Is that okay? Don't confuse this with this expression here. Is that okay? You have to do the difference between the inductive reactance and capacitive reactance first before you square whatever you get from there. I hope I've communicated, right? Okay, now we know the impedance in this circuit, the opposition to the flow of current in this RLC series AC circuit. All we need to do here now to get our peak current is to substitute that value here. Is that okay? It means that in place of this Z, you can actually copy this square root, R squared plus open bracket XL minus XC, close the bracket square. You can actually substitute it for Z here. Now, let us look at the root mean square current. Once again, going through the Ohm's law formula, the root mean square current will be obtained from the root mean square voltage and the opposition to the flow of current in this circuit, which of course that opposition we've already established it to be what? The impedance. Quickly take note of this, XL minus XC. XL is known as inductive reactance. And then XC is known as capacitive reactance. You could still hear another reactance there, is that also? Which means this term in bracket here is actually known as reactance. Are you following, right? It's actually known as what? Reactance. And we use X for it. So if I decide to replace XL minus XC with X, which we call reactance, then of course this formula can still take this form, Z equal to square root of R squared plus X squared. For short, are you following? For short. You have to remember that your X there, reactance, is equal to XL minus what? XC. Let us now consider the voltage across each of these elements here, and as well define our impedance as well as reactance. Then we'll consider the phase difference between the current and the voltage in this RLC series AC circuit. Let us now establish the voltage across each of the elements you have in this RLC series AC circuit, and of course the total voltage in the circuit. We've got these equations or formulas on the board here, equation 4 to 7. The first is the voltage across the resistor. Now, this is the resistor in this circuit. For one thing, you want to take note of the fact that these elements are connected in what? Series. And because they are connected in series, it simply means that the same current flows through them. Is that okay? So these three elements, in establishing their voltage value, take note that the current will be the same all through. Now, how do we get the voltage value? Once again, rely on the ohmic equation. Is that okay? The ohmic equation. Now, voltage is equal to current times resistance. Here, resistance there is the quantity that is opposing current in that circuit. Hence, for this AC circuit here on the board, the voltage across the resistance is equal to current times the resistance value. The voltage across the inductor is the total current times the inductive reactance XL. Remember that the inductive reactance XL is the quantity that opposes current when you're dealing with what? Inductor. And the XL there is given as 2 pi FL. That's the formula here. Already from our previous class, we already established this formula, right? XL. Next is the voltage across the capacitor. But the voltage is the current flowing through. That's the total current multiplied by the capacitive reactance X sub C. The X sub C is given as 1 all over 2 pi FC, which was already established in a previous class. That gives us equation 6. Then the total voltage in this circuit, because this total voltage applied across this AC circuit, that is what is shared among these elements, VR, VL, and VC. So the total voltage is obtained from the total current multiplied by the total opposition to the flow of current. And the total opposition to the flow of current in this circuit is the impedance, Z. This formula we established previously as Z equal to square root of R squared plus, open bracket, XL minus XC, close the bracket, raised to power 2. So this formula is important for us to take note of them. Now, let us look at these definitions in the board: the definition of impedance Z, the definition of reactance X, and the definition of phase. Impedance is simply the total opposition to the flow of current in a circuit containing a resistor, an inductor, and or a capacitor. Please, this definition is quite important. You see, we approach the definition saying that impedance is opposition to flow of current, total, overall, is that okay? Opposition to the flow of current in a circuit that contains either a resistor, inductor, and a capacitor, or a resistor with an inductor in that circuit, or a resistor with a capacitor in that circuit. What does that tell us? That simply means that for us to talk about impedance, there must be a resistor in that circuit. If you have a circuit containing only inductor and capacitor, the opposition to the flow of current there is not called impedance. It's not called impedance. The reason there is no resistor in that circuit. So take note, for you to use the term impedance, there must be resistor in that circuit. Either all these three elements are there, or you have RL in it, or you have RC in it, which was the reason why I used impedance. In our previous class, when we were calculating the opposition to current flow in an RL circuit as well as in an RC circuit. We move on to reactance, X. Reactance is defined as the opposition to the flow of current in a circuit that contains an inductor or a capacitor, or an inductor and a capacitor. So you took note of something here. Resistor has nothing to do with that here. Is that okay? When a current is being opposed by an inductor or capacitor, or by both of them, then that opposition is called reactance. Resistor has nothing to do with that. Phase. We've been using that word since. Phase. What is it? It is simply the state of vibration of a periodically varying system at a particular time. The state of vibration, the level of vibration, the value that that system attains at any particular time. That is what we refer to as what? Phase. Now, we use the concept of phase angle to help us get to know whether the two vibrating systems, if they have the same value, that is to say, if they approach their minimum, their maximum, or their zero value at the same time, or if one approaches its maximum or its minimum or its zero level before the other. For us to determine that, we talk about the phase angle, which is given as Wt. And Wt here is the same as 2 pi ft. W there is 2 pi f. T is the time domain. And I've decided to refer to all these things as phi, just like theta. So 2 pi ft is also the same as an angle phi. Or you can use Wt. When talking about maximum and minimum value, what do I mean by that, or zero value of the system? You may have encountered diagrams like this. Maybe we have something of this form. Alright, let me do a sketch like this. Now, in this sketch, this peak, this highest point, alright, is called the maximum value, max. Then you come to this. This is the minimum value, min. Then of course, this point is our zero value. That is our zero value. So if two systems, you can put this down please, what I'm about to say here. If two vibrating systems are in phase, because we've used that concept before, they are in phase, they are out of phase, you know. If two vibrating systems are in phase, it simply means that both of them, they attain, they reach their maximum, their minimum, and their zero value at the same time. But if they are out of phase, it means that one of them will reach its maximum or its minimum or its zero value before the other one. And if you sketch a graph on that, you will see that there will be no coincidence, right? No point of intersection simultaneous meeting by these two vibrating systems. Then you can say that they are out of what? Phase. However, take note that in an AC circuit, these two vibrating systems must have the same frequency. Is that okay? They must have the same frequency. However, they may or may not be in phase. Now, we shall establish the phase angle formula next. In this video, we now want to look at the value of the phase angle. Remember, it was stated previously that in an RLC series AC circuit, it has been found that the current and the voltage are out of phase. It means that the current and the voltage, they do not reach their maximum or their minimum or their zero value at the same time. One of them reaches its maximum or minimum or zero level before the other one, which means there is concept of lagging and leading in this circuit, RLC series circuit. But before we explain that, before we explain the quantity that leads and the one that lags, I would like us to look into the phase angle formula. Mathematically, the phase angle formula is giving us tan theta. Okay, this is phi, right? Tan phi. There, of course, you know that phi is 2 pi ft is equal to x all over r. And what is our x? The x there is the reactance. The x there is the reactance divided by the resistance. So this equation 8 gives us the value of the phase angle. Of course, if you make phi subject of the formula, it's going to be the arc tan, that is tan inverse of x all over what? R. And don't forget that we've already established that x is equal to xl minus what? xc. So you could see that in this equation 9. Equation 9 is simply another form of equation 8 by considering this vector diagram on the board here. Okay, now having explained this equation 8, I'd like us to quickly look at the vector diagrams we have on the board here. Okay, we are using the resistance as our reference. We are using the resistance as our reference. The reason is that in an AC circuit, you would recall that if it is purely a resistive AC circuit, then the current and the voltage are said to be in phase. No one leads the other, hence there is no one that lags on the other one. The current quantity and the voltage quantity are in phase. They reach their maximum, minimum and zero level at the same time. That is why we are using this as our reference value, VR. Okay, now if this is VR, we have VL facing up and then VC facing down. That is voltage across the inductor, voltage across the capacitor, voltage across the what? Resistor. Now, if we transfer this V sub C up, it's going to become minus. It's going to become what? Minus. So we have VL minus VC. That is to say, if we decide to say, okay, the two lines, VL, they should face up. VL, they should face on that. Remember that this VC was facing down before. So if eventually it now faces up, okay, it was facing down, let me put it this way, then it is now reversed. It's now reversed to face up. It therefore means that this part is going to give us VL minus VC because of the change in direction. Is that okay? Because of the change in direction, then this is going to give us our VR as before, the reference voltage. From there, go to diagram B. If you draw the diagonal of these, all right, will now be the total voltage, which of course you know that this height is going to be the difference between VL and VC. Is that okay? And we can actually get our angle, which is phi, as you saw here. Tan phi will be equal to opposite over adjacent, TOA. Alright, which is why we now have VL minus VC all over what? VR. R. Now, when we translate this into the opposition to the flow of current diagram, that is the reactance diagram, okay, the impedance diagram, is that okay? This. You now notice that it's going to follow the same format. The vertical is going to be XL minus XC, which is our reactance. The horizontal, the reference point, is our resistance. The diagonal, alright, which happens to be the hypotenuse of this, will now be the combined effect of the position to the flow of current offered by resistance and the reactance, which of course we call the what? Impedance. You could see how we actually got that equation for impedance, because one could use Ohm's law here. Oh no, one could use Pythagoras theorem here, right? Pythagoras theorem, that square of the impedance will be equal to the square of the reactance, which is XL minus X in bracket square, plus the square of what? The resistance. Making Z subject of formula, you take square roots. Is that okay of both sides? That's actually how we obtain our impedance formula. So from this diagram as well, too, we can get our phase angle to be XL minus XC divided by what? R, knowing that the numerator from equation 8 is reactance, which is of course the difference between the inductive reactance and the capacitive reactance. Going back to the vector diagram here for the voltage, one could also establish the Pythagoras theorem in terms of the voltage, and this is how the formula is going to look like. So that total voltage squared, which is the hypotenuse here, is going to be V2 squared, right? That's meant to be VR, V sub R squared. Is that okay? Plus VL minus VC in bracket squared. Just simply applying Pythagoras theorem here, you get this. To get the total voltage, you can actually take square root of both sides, just like I explained for the impedance. So that's just the explanation of the equations on the board. Of course, we've been able to establish the phase angle difference. Now, there is a point I want to make here, and please put it down. Okay? In an RLC series circuit, when do we know whether current is leading or whether current is lagging on the voltage? It all depends on the value of phi. It all depends on the value of phi. I'm going to quickly make an analysis here. Are you following, right? If phi is negative, it simply means that XL is less than XC. And for XL to be less than XC, all that tells us is that the current will be leading the voltage. So I'll write I leads voltage. You know that for XL, inductive reactance, to be less than XC, it simply means that the RLC series AC circuit is more capacitive than being inductive. Is that okay? It is more capacitive. And that being the case, it therefore means that current will be leading on voltage. Take your mind back when we treated an AC circuit containing only capacitor. We stated in that case that current leads voltage and voltage lags on current with a phase angle difference of pi over 2 radian, which is equivalent to 90 degrees. Now, in the other way around, if phi is positive, I'm sorry that I have to really constrict my writing here. Is that okay? If phi is positive, I'm saying what I'm writing here, so you can actually make a note of it. If phi is positive, that's the phase angle. That simply means that XL is greater than XC. For XL to be greater than XC, the information we get there is that the RLC series AC circuit is more inductive than being more capacitive. And for the fact that it is more inductive, that simply means that current lags on voltage, and hence voltage leads current. That was what we explained when we treated an AC circuit containing only what? An inductor. I stated clearly there that current lags on voltage and voltage leads. So in the case where phi is positive, SL is greater than XC. Therefore, current lags voltage. So please, what I just said, Put it down, very important. That is how we get to know in an AC circuit containing resistance, inductance, and capacitance, when does current lead, when does current lag, when does voltage lead, and when does voltage lag. Next, we shall consider the power in an AC circuit. Let us now look into the type of powers, right, in an AC circuit. Now we're going to treat three of this power that can be encountered in dealing with an alternating current circuit. The first, we'll look at the average power, P average. So have definition here on the board. The average power is the product of the effective current and the effective voltage multiplied by the cosine of the phase angle between them. That's the phase angle between the current and the voltage. Remember, talking about effective current and voltage, you're referring to what? The root mean square current and voltage. So it simply means that average power in an AC circuit is equal to root mean square current times root mean square voltage times cosine of the angle between them. Equation 8 on the board here gives us the formula of the average power. Consider I RMS, that's root mean square current, times V RMS, which is root mean square voltage multiplied by the cosine of the phase angle phi between them. Let us now look at that quantity cos phi in that equation 8. Cos phi. This cos phi is known as the power factor, a very important quantity, because that cos phi can help us know if the AC circuit is purely an inductive circuit, purely a capacitive circuit, or purely a resistive circuit. So how will that help us? We're going to find out as we move on, alright? Especially when we talk about the next type of power, power absorbed. Having defined cos phi as our power factor, the power factor mathematically is obtained from resistance and impedance. Cos phi, which is the power factor, is equal to resistance divided by the impedance in this circuit. And of course, not to forget, remember the impedance Z is equal to square root of R squared plus, open bracket, XL minus XC, close the bracket, square. That gives us the impedance. Alright, equation 9 defines our power factor. I use PF to represent that. We now want to talk about power that is absorbed in an AC circuit, power absorbed. Alright, the power absorbed is that power in the resistor. The power in the resistor, not in the inductor, not in the capacitor. When does the concept of power absorbed come into play in the study of AC circuit? It happens when the phase angle between the current and the voltage is equal to 90 degrees. Alright, so take that. When the phase angle phi is equal to 90 degrees, the power factor will now become cos 90, and of course we know that cos 90 is equal to what? 0. Cos 90 is equal to what? 0. Now, once cos 90 is equal to 0, go back to equation 8, let's look at something. It means that cos phi, cos of the phase angle is 90 degrees, you get cos 90, which is 0. 0 times the root mean square voltage times the root mean square current will still give you what? 0. So what does that tell us? That in such a case, the average power will be equal to what? 0. So once the average power in that case is equal to 0, we now talk about the power absorbed. And in such case, the power absorbed is giving us the square of root mean square current multiplied by the resistance. Because this power absorbed is the power absorbed in the what? Resistor. You can quickly put this down place, what I'm about to say next, because it's not on the board here. When the power factor of a device is equal to 0, of course that happens when phi, the phase angle, is 90 degrees. What does that mean? It simply means that that device is either a purely resistive circuit or a purely inductive circuit, or a purely what? Capacitive circuit. Alright? Now, when such happens, the power dissipated in the inductor will be 0. The power dissipated in the capacitor will be 0. What does that mean? It simply means that no power is dissipated in the inductor in that case when the power factor is 0. Of course, that is when the phase angle is 90 degrees. It means no power is dissipated in the inductor. No power is dissipated in the capacitor. These two elements, they are elements that dissipates power. Are you following, right? So when the power factor is equal to 0, which is when the phase angle is 90 degrees, no such power is dissipated in this inductor and capacitor. However, for a purely resistive circuit, there will be power absorbed in such case. And the power absorbed in that case is given by this equation 10, which is P equal to I squared RMS times the resistance value. I hope you got that right. Alright, now let's move on to the next type of power here, the instantaneous power. The instantaneous power is simply obtained from the product of instantaneous current and the instantaneous voltage. That gives us equation 11 here. I instantaneous, I use INST for instantaneous multiplied by instantaneous voltage. That defines our instantaneous power. We shall now define resonance, a phenomenon that takes place in an AC circuit under a certain condition. Of course, talk about the resonance frequency and the condition that leads to resonance in an AC circuit.